We'll talk today temperature measurement, and this lecture is in continuation of my earlier lecture where I have said the temperature measurement by thermocouple, and in brief towards the end of the lecture I have introduced to the another method of temperature measurement, that is by using the radiation of an object. In very brief introduction over there I have said that the intensity of radiation, it depends upon the temperature of the body. The body at higher temperatures, it emits all wavelengths. However, the intensity and the wavelength, it depends upon the temperature. The total energy intensity of all wavelengths is given by Stephens-Boltzmann's law, that is, intensity of radiation is proportional to the fourth power of absolute temperature. That is what I have said. I have also said that this is a non-contact type of temperature measurement. Thermocouple makes a contact with the medium for which the temperature is to be measured, whereas in the pyrometry you do not make any contact, so it is a non-contact type of temperature measurement. Now, the principle of this, it depends upon the intensity of radiation, it depends on temperature and wavelength. At a given temperature, the total energy emitted, say at a given temperature, the total amount of energy radiated by all wavelength of a black body is given by Et, that is equal to sigma T to the power 4, where sigma is Stephens-Boltzmann's constant. Stephens-Boltzmann constant, and its value is 5.67 into 10 to the power minus 8 watt meter square Kelvin to the power 4, and T is in Kelvin, where Et is total energy emitted per unit area. I mean, this is a famous Stephens-Boltzmann law, and I think you are all aware of it. Now, if we consider monochromatic wavelength, and say we try to make a plot of monochromatic wavelength or the intensity of the monochromatic wavelength with the wavelength, then the total energy will be the area under that particular curve. For example, say if we plot here, E lambda, say for example in watt per meter square, and we plot against wavelength, and the wavelength, let us take lambda into 10 to the power minus 6 in meter. We start from 0, 2, 4, 6 and so on. So, the variation, it depends on temperature. This is a typical plot of intensity of monochromatic radiation with the wavelength for different temperature. So, this is for example T, say let me take approximately equal to 1400 Kelvin, because I have not given any scale on the y-axis. So, this temperature just represent a qualitative fashion with reference to, if I take at lower temperature, let us take for example T, that is equal to 1000 Kelvin, 1000 Kelvin, and in between that is T, that is equal to 1200 Kelvin. So, what we see from here, that the radiant energy, what we note from here, that the radiant energy is spread all over the spectrum, all over the spectrum. Say for example, if you take a curve for T is equal to 1400 degree Kelvin, then you will find that the total amount of energy, it is spreading from this particular wavelength to this particular wavelength. Similarly, if you see for 1200 degree Kelvin or 1200 Kelvin temperature, then the radiant energy contains wavelength of all intensities. However, the intensity is different, for different lambda, Intensity also depends upon the temperature. So, if you note from here that the energy content with lower wavelengths, very very low, then 2 or 1 or say 1 micron meter, it is extremely low, where most of the energy is contained in between the middle range of the wavelength. So, what is important here is that the intensity of wavelength is different for different lambda, and also it varies with the temperature. Say higher is the temperature, the intensity of monochromatic intensity is also higher. Now, say if I just enlarge this particular curve and I try to represent in another fashion, where I superimpose the region of various wavelengths, say I will take here 0.1, somewhere I take here 0.4, somewhere I take here 0.8, 2 and 4, and here I take E lambda, say let me go from here 10 to the power 4 to 10 to the power 6, 8, 10 and 12. So, between 0.4 and 0.8, this is the visible range, and from here this is the infrared range, that is the frequency beyond 0.8 micron meter, it corresponds to infrared region. Between 0.4 and 0.8 they correspond to the visible region, and from here onward they correspond to ultraviolet region. Then violet, then X-rays, gamma rays and cosmic rays of very very lower wavelength. So, here is the lambda in micron meter. So, if we show the variation, for example, at very high temperature, say if I plot for very high temperature, then this particular curve, just I will say a temperature of very high 5760 Kelvin. On the other hand, if I take for example 2000 Kelvin, then it has this particular variation, 2000 Kelvin, and say for example if I take 1000 Kelvin, then I have this sort of thing here. This is for 1000 Kelvin. So, this is the variation of monochromatic MSE power, E lambda in watt per meter square with lambda and temperature for a black body. For a black body, that is here watt per meter square. Now, if we analyze this particular curve, we note that most of the energy, most of the energy, it lies between 0.5 to 10 micron meter. Now, the intensity E lambda of a black body, that can be given by C1 lambda to the power minus 5 upon E C2 sigma T minus 1 in watt per meter cube, where lambda is the wavelength in meter, T is in Kelvin, C1 is a constant whose value is 3.69 into 10 to the power minus 16 watt upon meter to the power 6. C2 has a constant 1.44 into 10 to the power minus 2 meter Kelvin, and sigma is again a Stephens Boltzmann constant. Now, this is the intensity of monochromatic radiation as a function of lambda and temperature. This is perfectly for a black body, but in real we have a sort of a real body, and we have to consider for emission from real surfaces by considering a quantity emissivity, and as such ET, total amount of radiation that will depend upon for a real surface to the power 4, and similarly E lambda for a real surface epsilon C1 lambda to the power minus 5 upon E C2 sigma T minus 1 watt per meter cube. Equation 1, this is equation 2. Now, if we want to compare the E lambda versus lambda for black and real surfaces, then it looks something like this. I am just showing a schematic one. This is here E lambda and this is here lambda. So, for a black body, the variation is something like this. This is for black body. Whereas, for real body, this is the case for real body. And for gray body, the measurement shows this sort of, this is for the gray body. So, all that it says that the monochromatic intensity of radiation or in general intensity of radiation is affected by the emissivity of the surfaces. Therefore, in order to apply the concept of radiation for temperature measurement, the emissivity of the surface is very important, and in this particular context you see the emissivity of real body and a gray body is not very different, but however they are lower than the black body. So, the radiation pyrometry, in fact, it is based on the equations 1 and 2. That means, the radiation pyrometry, it is based upon the how better you can see the monochromatic radiation, or how better you can judge the radiation intensity. Now, say some points to note. Some points to note. Point number 1, say high intensity wavelength region, high intensity wavelength region, it lies between 0.1 micron meter to 10 micron meter. What I mean to say is that at any temperature, the radiation will be emitted of all wavelengths. So, that is the important thing over here. Say here, say 0.1 to 0.4 micron meter belongs to ultraviolet, then 0.4 to 0.7 micron meter, that is the visible range, and 0.7 micron meter, say above 0.7 micron meter, that is the infrared region. Now, as temperature increases, radiation becomes stronger towards a smaller wavelength. Now, the practical applicable region, say practical applicable region for all temperature is in between 0.5 micron meter to 8 micron meter, which correspond to visible as well as infrared range region. Second important thing is to note, since we are going to measure the temperature by radiation, that means we will be comparing the radiation emitted by the object with some standard intensity of radiation. So, it is obviously most important that the path of the radiation should not be hindered by dust, by gases and so on. So, second important point, the instrument which you are going to build up, say instrument, it must be protected, to avoid dirt, dust and grease which are present in the environment, because ultimately the radiations of a body of which the temperature is to be measured, we will be seeing those radiations through a window. That means, we have to provide a window so that we can see the radiations emanated by the body. So, for that purpose, anything which comes in between the radiation and the window, some amount of radiation will be lost and you will not be able to measure the correct temperature. Another important thing is that the material of the window, because you are seeing through the window and the window should have a very high transmissivity. That means, it should be able to transmit all radiations of all wavelengths to your eye for comparison purposes. So, again third important thing over here, third thing, that windows are provided to see the radiating body, and here the transmissivity of the material of the window body is important. Say, for example, all optical materials have their own transmissivity, that is, they allow only particular wavelength to pass through sufficient intensity, and for some of the wavelengths they are opaque. So, it is important that you should have selected an optical material which transmits most of the wavelength which is coming from a body for comparison purposes. So, here for example, if I say transmission power transmission power of some selected optical materials can be shown. Say, if I plot here, there are very different type of optical materials are available. So here we take the wavelength region 0.4, 0.7, this is the visible range, and here I will take transmission power. I take here transmission power or transmissivity, and here is the lambda. So, for example, if I take, and this region is, this is the, say 1, 2 and 3, 1 ultraviolet, second visible, and third infrared. So, the, say for example, the calcium fluoride, if we use as the optical material, then the calcium fluoride, it has this sort of behavior for transmissivity. So, this curve is for when calcium fluoride is used as a window material. For example, if we use the barium fluoride, then the barium fluoride is this one, and this is for the barium fluoride. And if we take glass, which is popularly available, then glass has this sort of behavior. So, what we note from here, the following points. Point number A, say glass, for that matter quartz, crown glass or pyrex, have good transmission in ultraviolet and visible region, but they are opaque to infrared. Since you are seeing on the infrared side, it is just increasing. So, the glass windows are of no use at lambda greater than 2.5 micron meter. Similarly, B, point number B is that, say barium fluoride and for example zinc sulphide, they have 60 to 80% transmission in infrared region. In infrared region and visible region. And C, the calcium fluoride has overall good transmission. So, the selection of the material of the window is important in order to measure the temperature of the object correctly, because the most important point in selection of the material of the window, that it should be able to transmit most wavelength for comparison purposes. Now, third important thing is that the radiation parameter will require a sensor which can detect the incident radiation and generate an electrical signal. So, one does require a sensor which can sense the so-called the incident radiation, and it can create an electrical signal. Now, here sensors, thermal detectors are used, thermal detectors can be used as sensors, which are consist of different types of thermocouple element wires, and second the semiconductor sensors. Semiconductor sensors. And these semiconductor sensors are based upon use of silicon, lead sulfide, indium NT, monide, etc. Now, the response of semiconductor sensors is instantaneous compared to thermal sensors, but it is selective to particular wavelength. For example, silicon is suitable for 0.8 to 0.9 micron meter wavelength. Now, this you can correlate with the temperature. Similarly, lead sulfide is suitable to 1 to 2 micron meter. So, that is an important thing. Fourth important thing is that radiation pyrometer should be kept away from the dust particles, because they will scatter the radiation. Any material or any gases which can scatter the radiation, that will affect the temperature measurement. Therefore, the radiation pyrometer should be away from all these gases or dust particles which can scatter the radiation. Also, the radiation pyrometer require emissivity correction. Now, since the emissivity epsilon is a function of surface condition, this is a basic which all of you know, surface condition, temperature and wavelength. Therefore, the correction is needed. So, during the measurement, for example, you are using steel, and if it oxidizes, then when it does not oxidize, then the emissivity correction has to be applied in order to make a correct temperature. Now, there are several types of radiation parameters are built based on the concept. Now, if I summarize the conceptual part of the radiation parametry, then I can summarize as follows. Essentially, you need a sensor. A sensor should be able to detect the incident radiation, and these incident radiation, after detecting by the sensor, it creates an electrical signal. Of course, these that sensor should also give an electrical signal, so that the temperature can be measured. So, based on this, we have one type of pyrometer, The one is the disappearing filament pyrometer. Disappearing filament pyrometer. Now, when you think of a pyrometer, it should have all say different arrangement of the lenses, mirrored, so that it can direct the beam to the sensor. So, in a disappearing filament type of pyrometer, it looks something this way. So, this is the pyrometer body. This is the so called pyrometer body, and here we have a glass window. So, this is a glass window. Which is seeing the radiation at temperature T and the intensity of radiation of all wavelengths, that is ET. Now, we further require the so called focusing optics. You have to focus the beam. So, these are the this one and this one, they are the focusing optics. Focusing optics, because the radiation which are coming, they have to focus the beam. Naturally, one does require a sort of filter. So, this is a filter, this one is a filter which filter all unnecessary type of things, and then you have a sort of a so this I will put as a filter. Then you have a tungsten filament, that is the source with which the intensity of radiation will be compared. So, this is a filament, this is a filament, and say this one is the tungsten filament, which is, for example, at some temperature TL, just a material. Now, you do require something to see, and there we have the eyepiece. There you have the eyepiece, and it again has lenses and mirrors for focusing purposes. So, this is the eyepiece, and here say we have the this I am not showing, it is simply the millimeter, which is calibrated in degrees Celsius, and this is the electric circuit. This is the electric circuit to change the intensity of the tungsten filament depending upon the intensity of the radiation emitted by the body. So, this is in fact very simple construction of disappearing filament pyrometer. Now, if you see, the radiation is emitted from a body, radiation travels this way. The objective of the focusing optics is to direct the beam, and unnecessary things are being filtered out, and the intensity of the beam is matched by the intensity of the tungsten filament, and whose intensity is adjusted by an electrical circuit, so that when both the intensities are matched, then a reading is obtained on the millimeter, which you can get a reading in terms of ampere also, or that millimeter can be calibrated in terms of temperature. So, that is what the function of the disappearing filament type of pyrometer. Now, another type of pyrometer, that is the radiation pyrometer. Radiation pyrometer. Another type of pyrometer, that is the radiation pyrometer. Now, the radiation pyrometer, it also has one sensing head, or you can also call it to be a detector. That means, it will detect the intensity of radiation. And then one is the sensing head, and second you have electronic part. and the electronic part they adjust to compare the intensity of radiation of the object. So, the sensing head it is either a thermal sensor or they are semiconductors. They are semiconductor. Let us see what a thermal sensor is. Now, in fact, thermal sensors here they consist of several thermocouples. They are arranged in series. Thermocouple could be, for example, chromolelumal. Normally 8 to 10, they are situated radially and connected in series. So, this is the schematic representation of a thermal sensor. This one this is a mica disc. And these two, they are say connecting prongs to cold junction compensation, and to indicator. These things are, that one is the blackened hot junction near center, and these are the thermocouples. So, that is how a thermal sensor looks, and the thermocouples, they are arranged in series for temperature measurement. Another thing is semiconductor sensors. They have a response time is very short, around 0.01 to 0.05 second. However, the thermal sensor may have a longer response time, whereas semiconductor sensor may have very small response time because of their electronic sensitivity. Now, depending on the optics, which is used to see the radiation, they can sense, or the semiconductor sensor can sense (0.65) to 10 micron meter wavelength intensity of radiation. Between this range, they can sense the intensity of radiation. They can be used up to 3500 degrees Celsius with an accuracy of of 0.75% full scale. Now, the sensors, they may be sensing a very narrow wavelength band or a broad wavelength band. That depends on the type of sensor which is under use. Normally, one can say that a radiation pyrometer based on the semiconductor sensing device, they can go for a very high temperature, they will be accurate as compared to thermal sensor. However, it depends on the other factors also, the type of window material and the environment, the whether the radiations are scattered or not. All these things affect the accuracy of the measurement of temperature by radiation pyrometry. Now, obstruction of the beam, obstruction of the beam, I mean say radiation beam, it can cause incorrect temperature measurement. As I have said, that the radiation intensity which is emitted by an object, it should not be hindered by any dust, dirt or the gases which can scatter the radiation. They all lead to incorrect measurement, and this obstruction of the beam may be due to presence of dust and smoke. Another important thing is a change in emissivity. Change in emissivity with time and temperature, because the surface is surface characteristics might have changed. That is an important thing. Third, the object is too small. Object is too small. Now, a radiation pyrometer, it will look something can be shown schematically by this. Say this is a sort of lens. This is a lens. This is a hot object. Put it, and it is emanating radiation, and then we have a sort of a mirror. This is a mirror, and the passing through the mirror, then again we have a lens which collects this thing, so this is how this one here the one. So this is, let me sign, this is the hot object. This is the hot object. This is the lens. This is the mirror. And this one is the adjustable eyepiece. Adjustable eyepiece, and from here this one is the so-called detector. That is, the beam through mirror is directed, and this detector, it detects the intensity of radiation, and from here it goes to, this is the temperature indicator. And this is the block diagram of a radiation pyrometer. A radiation pyrometer. Now, in this also there are two color pyrometer are also in use. Two color pyrometer also in use, and this two color pyrometer, it senses two different wavelengths. It senses two different wavelengths from the incident radiation. Incident radiation. Now, this is achieved by two separate detectors, or we take a rotating disc filter. That is, either we take two separate detectors, each for one for a different wavelength, another for a different wavelength, or we take a rotating filter, and according to the wavelength we adjust the rotating filter. So, it is, for example, if we have an object which is emanating radiation at temperature T, wavelength lambda 1 and wavelength lambda 2 are fallen on a mirror, on a lens, and this one we have the so-called, this is the double sensor. And this double sensor, it senses two wavelengths at the same time. Two wavelengths at the same time. This is some sort of a, what you call as a detector which can sense two different wavelengths at the same time. Another, say we have a rotating filter, say we again have an object here which is at temperature T, emanating radiation lambda 1 and lambda 2. It goes to the focusing optics. So, we say this one and this one, they are the focusing optics. Focusing optics, and here it goes to a single sensor, and somewhere here we have a rotating filter wheel. It looks something this way. This is a rotating filter wheel, with alternate lambda 1 and lambda 2, and it has so called the various Now, if we use this rotating filter, now if we want to compare these two type of mechanism or two type of instrument which are used under the head two color pyrometer, then we can see that in a double sensor the time lag is very small as compared to in case of rotating filter wheel, it has a time lag. It has a time lag because you have to adjust the wheel for sensing the wavelength, whereas in case of double sensor we do not have the so called this type of time lag. So, this is in short what I have tried to give you an over idea in this lecture as well as in previous lectures, the various methods of temperature measurement. To summarize, in one we have used the thermocouples, which is based on the use of two different materials. When they are joined, they produce an electromotive force. This is one mechanism. This is a principal mechanism. On that basis, several types of different materials have been searched and several types of thermocouples are made. Another one is the pyrometer, which is based on the measurement of intensity of radiation, or precisely we can say which is based on the comparison of the intensity of radiation emanated by the object with the standard radiation, and that we get a temperature. Thermocouple is a contacting device. I mean, it contacts the medium, whereas a radiation pyrometer, it does not have any contact. It is a non-contacting type of temperature measurement. So, depending on the situation, one can use thermocouple as well as radiation pyrometer. For a distant measurement, maybe thermocouple, maybe the radiation parameters are good. So, I tried to give you an blick about the temperature measurement.